Hello everyone. Today we are going to present our final term project which is about steel surface defect detection. First let me introduce my group. Mastan Phaluri, Naresh Patel, Karim Tergioglu and myself Jitendra Prajapati. Here is how we are going to approach the presentation. First of all I will give project overview. Next is dataset overview, data analysis and feature engineering, models, prediction using CNN, models evaluation, challenges, and finally the conclusion. Project overview. Steel is one of the most important building materials of modern days. Quality of steel surface is essential for steel industry and detecting the quality issue is very challenging. So we decided to take up the challenge to detect and classify the surface defects using machine and deep learning. Our main objective is to accurately classify the surface defects and apply the knowledge we gained during the semester. We used image pre-processing techniques such as filtering and extracting the surface features from images to train and classify the defect type. We used accuracy metrics to evaluate the models. The steel surface defect dataset is available online at Northeastern University NEU database at provided link. The NEU dataset contains 1800 grayscale images. A few samples are shown in the figure below. Each image is 200 by 200 pixel. The images given in the dataset are in the .bmp format. It has 6 types of typical surface defects of the hot rolled steel strip. The different type of defects are rolled in scale, patches, crazing, pit surfaces, inclusion and scratches. We did some data analysis and feature engineering. As below graph shows, we can see there are 300 samples for each type of defect. So we can say that our data set is well balanced. So it justifies the use of accuracy metrics to evaluate the models. Methods used for feature engineering. The problem here is related to surface detection and it's very diverse and complex. Therefore, we decided to extract features such as contrast, dissimilarity, homogeneity, energy, and angular second moment. It's also called ASM. To extract such features, we use GLCM method. It's called gray level co-occurrence matrix. GLCM can be described as two-dimensional histogram that counts the number of co-occurrences between each pair of grayscale levels according to distance between them. The SK image dot features dot gray co-matrix is used to calculate GLCM. Also, SK image dot features dot gray co-props is used to calculate texture properties of GLCM. It returns contrast, dissimilarity, homogeneity, energy, and ASM. Here are the steps to calculate the GLCM, which are provided in book called Practical Computer Vision Application using deep learning with CNNs with detailed example in Python using TensorFlow and Kiwi. Flowchart image is showing in the steps. First step, if the input is grayscale or binary, use it directly. If it is color image, convert it to grayscale or just use one of the channel if appropriate. Second step, find the total number of intensity level in the images. If the number is L, then number this level from 0 to L minus 1. Third step, create L time L matrix where both rows and columns are numbered from 0 to L minus 1. Fourth step, Select appropriate parameter of GLCM, distance and theta. And final step, find the co-occurrences between every two pairs of intensity levels. We can see in the figure 1, the image A is the original image, which is a color image. B is the matrix of image. C is the initial GLCM where distance equal to 1 and theta equal to 0 degree. And D is normalized GLCM where distance equal to 1 and theta equal to 0 degree. To train CNN, we use data augmentation technique. Data augmentation strategy that is used to increase the size of training dataset by creating modified images without collecting new data. Example of data augmentation techniques are rotating, cropping, padding, flipping horizontally or flipping vertically the images. In the image we can see that one of the letter 6 has been flipped, cropped, and it has been after this it has been applied to the CNN network where it will give a better result. Now let's talk about models. The table shows the model which we have used to classify the defect detection. Different classifiers such as k nearest neighbor, random forest classifier, decision tree with boosting, and support vector classifier will be compared, and also convolutional neural network will be used to classify the defect. Here are the graph shows the tuning of the hyperparameter. For KNN model, k equal to 5 gives the best accuracy. For random forest model, it gives best accuracy when it reaches to 34 number of trees. We have used AdaBoost classifier with decision tree to get the best accuracy. When we reach k equal to 53, it gives the best accuracy. Now let's look at the CNN. We have used CNN with and without data augmentation. For CNN, we extracted images in 3-dimensional array where channels equal to 1. The graph shows accuracy and loss while training and testing the models. With data augmentation, we got 77% accuracy. Now let's compare the models. From the table, we can observe random forest gives highest accuracy of 88.30% and SVM is the lowest accuracy. It's 0.17%. We have extracted surface features using GLCM which is dependent on grayscale values and that may be negatively impacting the models. Now let's have a look at challenges we faced during the project. Usually RGB images shows better results compared to grayscale images. Intensities of the lights and resolution of images are impacting the model's results. Another challenge was to extract the features. We had to research a lot to extract images as we learned image processing in the last lecture. We extracted images in RGB channels due to which the model were performing very poor. After a while, we learned how to use CNN with grayscale images. And fourth one, when we applied data augmentation, the CNN model had only 14% accuracy. One of the reasons we were using the 3 channel instead of 1 channel, meaning RGB instead of grayscale images. Finally, the still defect detection was done using machine and deep learning. The feature of grayscale images were extracted using GLCM. The best model was random forest, and it has the highest accuracy. And learn And we learned how to use CNN with data augmentation for a small data set. In future, we are going to use the deep learning image processing technique in Kaggle competition. Also, we will build the co-occurrence matrix using gradient rather than intensity. Such matrix is called gray level gradient GLCM. Thank you very much.